Hello everyone, I'm Sun from the Chinese University of Hong Kong. Today I will introduce our work, Correlated Multi-objective Multi-fidelity Optimization for Address Directives Design. This work is cooperated with Ting Huanchen, Siting Liu Beiyu from the Chinese University of Hong Kong, Jing Miao from Synopsys, Jian Lichen from Fudan University, and Hao Yu from Southern University of Science and Technology. In this work, we focus on the optimization of high-level synthesis directives. High-level synthesis is usually abbreviated as HLS. It translates high-level programming languages, for example, C and C++, to low-level hardware description languages, under the guidance of HLS directives. For the same high-level descriptions, if we have different HLS directives, we will achieve different hardware implementations. In this work, for each application, a group of address directives is represented as a configuration vector X. Here's an example. There are two directives, and each directive is denoted as an attribute in the configuration vector X. There are various types of directives. For example, data flow, inline, pipeline, block partition, and etc. Here is the design flow. The inputs are address directives and high-level language descriptions. The whole design flow consists of 3 stages corresponding to 3 fidelities. They are high-level synthesis stage, logic synthesis stage, and implementation stage. Each of these 3 stages will give us some reports. Usually, the later stages consume longer running time, but have more accurate reports. So that's a trade-off, and we want to strike a balance between the running time and the quality of the analysis reports. If the results are at the lower stages are accurate enough, we will directly stop the design flow, even though we didn't run the later stages. In the design problem, there are multiple conflicting design objectives. For example, delay, power consumption, and results consumption. If we want to reduce the power consumption, we will tend to implement fewer logic units and consequently increase the system delay. To find the optimal solution in this kind of conflicting multi-objective design problem, we introduce the concept of Pareto optimality. That is to find some Pareto optimal points from the whole design space. Assume that we have 3 design objectives, FM, m equals to 1, 2, and 3. A value point y is represented as a value vector, f1, f2, and f3. For 2 value points yi and yj, we can say yi dominates yj if for any m, yim is greater than or equal to yjm. The non-dominated points are called Pareto optimal set. Here's an example. We want to minimize the power consumption and delay simultaneously. In the value space, the blue points are dominated by the red points. So the red points are non-dominated, and they are in the Pareto optimal set. The blank cells are dominated by the red points and called Pareto hypervolume. In the HS design problem, our target is to find the Pareto optimal points. In other words, our target is to find all of the red points in the design space. But there are still some challenges. Firstly, it's hard to predict the performance values accurately according to the objectives. Secondly, it's hard to characterize the complicated relationships between the multiple objectives. Thirdly, it's hard to balance the consumption of running time and the accuracy of the results. In this work, we want to develop a flexible and general method, strike a balance between optimization workloads and accuracy of results, and be able to characterize the complicated relationships between address directives and multiple objectives. Here is our solution. We choose to use spacing optimization, and the expected improvement is the acquisition function. Nonlinear Gaussian process is chosen to characterize the relationships between the reports of the multiple fidelities, and a Pareto learning method based on a novel correlated multi-objective model is proposed to handle the multiple objectives. Traditionally, researchers used the linear models to connect the reports of low fidelities and the reports of high fidelities. FML is the report of the low fidelity, and FMH is the high fidelity. Rho is a scaling factor, and FME is a narrow term. In our method, the reports of the low fidelity are concatenated as part of the inputs to the next high fidelity. Here, Z is a correlation function modeled by a Gaussian process model. To integrate the Pareto optimality with Bayesian optimization, a novel acquisition function, expected improvement of Pareto hypervolume, is proposed. At step p plus 1, we already have the dataset collected in the previous t steps. To sample the next configuration point xt plus 1 from the design space, we need to compute its expected improvement with respect to the Pareto hypervolume. In this example, the blank cells are dominated by red points, and the area of these blank cells is the Pareto hypervolume. If the green point is chosen as the next configuration point xt plus 1, then the light green rectangle is regarded as the improvement of the Pareto hypervolume. We will parse the whole design space, compute the expected improvement for each configuration point, and the point with the largest improvement is chosen as our candidate xt plus 1. We will then pass these candidate configuration points into the design flow, gather the reports, and then update the model accordingly. Now we need to combine the multi-fidelity model and the multi-objective model together. There are two dimensions, one for multi-objective functions and one for the multi-fidelity functions. Obtaining results at different fidelity cost different running time. To characterize this kind of difference, an additional penalty term is applied to argument EIPV as PEIPV. These penalty terms are hyperparameters, and we directly specify their values according to our experience. PEIPV can measure the balance between the running time and the quality of results. In other words, if the results of lower fidelity have achieved good results, we will only run the design flow to the lower stage to save time. But if the lower stage is unsatisfying, we'll also run the later stages to get better results. We conduct experiments on 4 traditional benchmarks and 1 DNN benchmark. To validate the performance of our method, all of the HS code and directives are compiled via Vivado HS to get the real reports. Real Pareto points are chosen as the reference point, and average distance to reference set is used as the quality metric. For the sake of fairness, our method and the baselines use the same input features. The Bayesian optimization in our method randomly samples 8 points to initialize the model and then conducts at most 40 optimization iterations. The results show that our method achieves the best ADRS performance compared with these baselines. Besides, the average values of the running time and the standard deviation of ADRS are also the optimal. Here we show a result example of our method on GMM and 3 objectives: power, delay, and consumption of lookup tables. All of these data are normalized. The results show that our method outperforms the 4 baselines. That's all of my presentation. Thank you very much for listening.